So our next presenter is Ning from Qualcomm, presenting on heterogeneous mobile processing platforms for computer vision applications. And Ning is Senior Director of Technology from the Computer Vision System team at Qualcomm Technologies. In the past 20 years, he's been working in speech coding and recognition, 3D graphics, and computer vision for embedded systems. Ning was an algorithm designer of a speech recognition system, Pure Voice VR, that was used in millions of CDMA handsets. He was a graphic software lead enabling OpenGL-ES in Qualcomm's chipsets, and he's currently responsible for R&D in both computer vision and GPGPU applications. He received his PhD from the University of Arizona and has been granted about 20 patents in speech, imaging, and graphics. Thank you.
Thanks, Brian. From Brian's introduction, you can tell I'm not the expert of computer vision, so bear with me. I just want to share a few personal opinion on the embedded system, how to use the embedded system to address the computer vision use case. And one of the challenge here is the heterogeneous computing, right? I agree with Chris' opinion in the DSP implementation to enable computer vision technologies. He made a lot of good suggestions, and I may touch those topics too. The topic today is a little bit too broad to be addressed by the technology today, but we will try our best, and also I'm expecting to have a good discussions with all of you after my presentation. It's the first time for Qualcomm to attend the Embedded Summit. So allow me to introduce the company briefly. Qualcomm is a telecommunication company to provide the 3G, 4G communication technologies. Also, we provide Snapdragon processors for a lot of smartphones. Within the Snapdragon processor, you have three big components that are related to computer vision or heterogeneous computing. The first one is the CPU. We have a quadra-core CPU there. One unique feature of the quadra-core CPU was each of the core can be configured with different frequency. It will be, you will see it's very important for low power implementation. The second component in the Snapdragon processor was the GPU. We call the Adreno GPU. It provides the gaming and the UI support, as well as GPGPU applications with OpenCL, the kernel standard. The last part I want to touch is DSP. Internally we call the QDSP. It's alternative solutions for low power implementation. So that will be the last component we are going to discuss today. So let's continue. When Jeff approaching us to talk about the embedded vision, right? In his opinion and our opinion as well, the computer vision in mobile device is a very important topic in the area. So I made a quick list of what can be done or can be considered with today's technology in a mobile phone. So object detection, tracking, classification, visual search, civilian camera, gesture recognition, OCR, AR, 3D reconstruction, and there are a few other topics. We have seen applications from the app stores or from a lot of third-party or OEM development, right? So I'm trying to give an example today what we can do with a phone. So this example is using 3D camera to take one picture of the user and create a 3D face of the user. So moving forward, you can have a 3D photo ID with your smartphone device. So we will exaggerate a little bit. So I got permit from this gentleman to use his image, and he said it's okay to morph my nose. So that's just one example what a smartphone can do today. The challenge of the computer vision in mobile, I put 3 things here, but I believe there will be more. Right? These 3 is very important to me, at least. The computing capability, right? Processor in a phone is not the processor in a desktop. It's quite different. You don't have a cooling system anywhere with the phone, right? Then it's resulting in the second thing we have to pay attention to, the power consumption. You don't have a power cable linked all the time, so you have to provide a low power solution. No matter what, any solution has to be low power solution in a phone. The last one is about the heterogeneous processing. We know not the smartphone, right, is with all kinds of different chipset. The chipset from Qualcomm, from Intel, from NVIDIA, TI, a lot of companies making chips, right? So the apps developer, they will hate to develop the applications case by case, phone by phone, right? They want to have a generic solutions that the application can be ported cross-platform. So the heterogeneous computing is really a good topic, will benefit everyone, apps developer, chip maker, and OEMs. Let's take a step back to look at the history of the multimedia in a mobile device. About, I think, 12 to 15 years ago, what is called multimedia in a phone? It's only speech, right? At the time, all thing we have to do is to encode and decode the speech. At the time, you have only 1 line of text to be displayed, but believe it or not, within the last 12 years, so many things has been enabled in a mobile device, right? So we are expecting the computer vision will be the next big factor, to be enabled in the phone to make the phone really a smartphone. So look at all those implementations, the history of the implementations of those technologies, right? They always start from a software implementation and later on move into a specific ASIC to do the firmware implementation with assembly coding, and later on, as the last phase, to come up with a hardware implementation for low power, for high performance. But for the computer vision today, we are still in the very initial stage. Most of the solution is based on software and firmware. There are hardware solutions, but those hardware solutions are for the specific use case. You may build up special ASIC to do the, let's say, palette recognition. Then for scan the cars and all those things, right? But for a mobile device, the phone is not designed for that. You just, take what you have to solve your problem. So we are still in the infant phase in the mobile device to address computer vision issues. But we have great potential. This chart here is about an example of a Snapdragon SoC. From here, you can see we have CPU cores, several cores, and 1 GPU core, and several DSP cores there. Right. Of course, there are dedicated hardware for video processing, dedicated hardware for picture taking. So those hardwares can be considered, in the pipeline of computer vision applications. So we have addressed what computer unit can be considered. CPU, DSP, GPU, ASIC, and FPGAs with different ISAs. the common questions from apps developers, we often get those questions as a chip maker. What results should be used in a multi-core system? You give me 4 CPU cores and multiple DSP cores and the GPU cores. What else? Which one is the best one to use? And also, they are, expecting to have the portabilities cross-platform. And also, they want to have a standard API. They don't want to use the specific ones. There are always cases the apps developer to come up with their own solutions and specific applications. But we actually, as a chip maker, we encourage the individuals to have a solution like that. But to address the issue at the system level, we really want to come up with a much easier solution. So we really want to, first, enhance the computing capability of the device. Second, provide low-power solutions. And since it's a computer vision, right, the camera is the sensor used here. To turn on the camera all the time is really very high cost in perspective of power processing. So how to come up with a low-power, always-on camera is one of the key component here we need to address at the system level. Then supporting the parallel processing with multi-core and also enable standard API is our focus as a company like Qualcomm or maybe other chip makers share the same opinions with me. The first component can be considered in a mobile device is the multi-core CPUs. So in the latest technology, right? For example, Qualcomm's Snapdragon processor has a 2.3 gigahertz 4 cores. It's very powerful. It's not far away from desktop, but the big difference here is you cannot expect to turn on all the cores at the highest speed all the time, right? The battery will be drained very quickly. So how to use it smartly? Use it when you have to use it, and turn it off after. So that's one of the key issues the application developer has to address. But in ideal case, we have to handle it automatically for the apps developer, right? So that's our one of the goals of the company to achieve that. So to accelerate the computer vision applications in multi-core CPU, the parallel processing is one of the key features or key method we have to, to provide to the apps developers. And also those features we really want to enable them seamlessly from apps development at that level of the effort. So I will address that issue a little bit later. So in the multi-core CPU system, one of the current solutions which is important for everyone, a few other speakers has mentioned this, the Ning instructions in the ARM architecture. So for example, you have a specific implementation here. There are 128 bits wide of the registrators. So if the input is in single precision of a floating point, you can only parallel 4 operations with the SIMD instructions, right? But if you can squeeze your input data into 8 bits, for example, 16 of the operations can be put in parallel. That's why you cannot assume there is a big high clock rate CPUs. I just let my algorithm go there, such as pick up implementation from OpenCV to run it, and you get the result. You can get the result, but with it will be with high cost in the power. So the optimization has to be done in a certain level. Let me show one example here to tell what a phone can do in the computer vision perspective. So the application here is things like this. We have a phone, and the phone can be used to track an object. We put the phone in a very simple robot from Lego. And the phone is communicating with the robot through Bluetooth. And from another phone, we give a command for the phone to track a face, right? The phone will drive the robot to approach the target automatically. So you give a robot an eye and a brain. So later on, the phone will send a picture to another phone with Wi-Fi. So a lot of things happen simultaneously here, right? So now he is giving a command to find the next face. So this project, we spent about 2 weeks to put together. We're not recommending to do things like this, but just to prove a concept. Why we call phone a smartphone, right? It's getting smarter and smarter. So the last part is the approaching the end of the table to find the face, and sometimes it hesitated to move because it is not sure, he got the right target. This is an example to do everything in a quadra-core CPU. So next, allow me to address, to discuss something in the GPU. We know the GPU is designed for graphics rendering, right? Graphics rendering is quite different from the, let's say, a lot of other multimedia case. In a typical graphics pipeline, right, you have a primitive compressed in a very small amount of data, right? To send to the GPU generates a big amount of pixels to fill the screen. Starting from VGA, now it's HD. Very soon it will be Ultra HD, 4K by 2K. So that's a typical, things GPU handles. But look at what computer vision is trying to achieve, right? You have an input image with millions of pixels. And those pixels, the resolution is getting bigger and bigger, right? But what you are trying to get from it is a summation of the information, very limited data to describe what you have learned from the scene. So those kind of process actually is reverse processing of a typical GPU is trying to handle. So, we shouldn't assume the GPU is really natively designed or friendly to the computer vision task. It is not. But it doesn't mean you cannot do anything with the GPU. We have a lot of cases to show how to use the GPU functions with OpenCL. Here are 2 examples. Those examples are demoing in the next room, so you can stop by to take a look. The first example is about object removal from an image. Assume you have some of the part in the image you don't like it. So you touch it and it will be gone. So the processing here is about, to find the similar patch in the scene to fill the hole there, right? Because you have no idea what is behind. We are making educated guess to fill the hole. Those kind of processing can be done because each of the patch is independent from others. All those tasks can be put there in parallel for GPU to handle. It's really a GPU-friendly application. Another application is object cloning. So by the way, all those things has been implemented in the Snapdragon GPU. So it's not an Autodesk on the desktop. It's just in the phone. You can do those quick editing. So while looking at the videos, I want to mention why I draw that chart there. So in a typical desktop, because you have a fan to cool the GPU down, the GPU sometimes is 100 times more powerful than the CPU. It happens, right? We have the experience like this. But in laptop or mobile device, the computation power between the CPU and GPU, the ratio is quite different. In the smartphone, typical smartphones, we measured, it's about the same. Compare one GPU core with a quadra-core CPU, depends on how do you configure the system, right? And also it's task dependent. It's about the same in many cases. So in our recommendation is to use both CPU and GPU simultaneously to pipeline your use case, to let the CPU do things that is really can be handled by the CPU and vice versa, and give the GPU right task. If you have an algorithm that totally is designed sequentially with the if then a lot of cases, so it's really hard to let the GPU to handle it. But talking about that, to reconstruct the algorithm itself is a kind of a challenge areas. We would like to see more activities from academia there to redesign the algorithm, right? To give the assumption that parallel processing is with the GPU is the unit you want to use, then redesign the algorithm to solve the same problem is something we really want to encourage the people to look at. The last component I want to talk about it is the DSP solution. DSP solution is a low power companion, in our opinion, to the CPU. It runs on a lower clock rate, and it doesn't have to support the standard OS. And we have a lot of L1 instruction data cache, and sometimes with L2 cache there. One let's say important case was with the DSP, you can always introduce new specific instructions, right? In an algorithm, if you find this instruction is very typical and it has to be implemented in the very inner loop, is your bottleneck, you can always introduce a new hardware implemented DSP instructions to speed it up. So in this example, to detect face, we used to do it in the CPU. The task itself took almost 100% of CPU, the power, if we do the detection every frame. When the face is, you have 10 faces, 20 faces showed up. But the face detection itself is not a task in most cases the application try to address. It's just a feature to enable other applications, right? So we really want to free up the CPU for other applications. when we move the task to the DSP, we free up the CPU first, then we saw a lower power of the implementation of the application. So in this page, I want to tell let's say the recommendation was for OpenCV. Chris mentioned this in his speech. It's really a good starting point. All professors or students in the universities use OpenCV, right? But we really try to enable OpenCV with the embedded system. It's very challenging. You don't have to support all kinds of data types. You don't have to support all the applications, different functions, right? There are 2,500 functions there. Some of them, only a few guys in the world to use. You really don't have to enable them. So an alternative solutions is such as from TI, they enable the VLib, and from Qualcomm, we enable something called FastCV. So it provides a solution with hardware acceleration. And also from Kronos group, the OpenVX has been discussed for a year. It's supposed to be an industry standard for embedded system. The last, I want to talk about the frameworks. The frameworks is really important. Why? In an ideal world, we need to, let's say, we wanted to address the issues of heterogeneous compute by the OEMs and the chip makers to free up the, to let the apps developer to think about how to come up with a real challenge or real attractive applications. Let them to look at the issue from the problem domain. And the chip maker and the OEMs provide solutions of heterogeneous compute to map those functions to specific hardwares. So how do we do it? I think OpenVX is moving to that right direction. First, we need to have standard APIs, right? The second, we have to make a list of predefined CV functions. Those functions has to be implemented by someone. Most likely it will be the chip maker like Qualcomm or the OEMs into different hardware component. Third, so we have to allow the user to define their own new applications, such as in OpenCL, everybody can define their own kernels to load it into GPU to run. Right? Then the last, the scheduler is very important to know runtimely which resource is available, which is not, then to schedule the task. So here is conclusion. The last word I really want to say is there is no perfect platforms today, and also there's no perfect solutions. Let's say no perfect algorithms available to solve all the issues. But what we can do is to find a well-defined problem, then to make a perfect solution. That part is really possible. Okay. So any questions?
The platform has CPU and GPU and media processing DSP.
Yeah.
Can you provide any comparison on the relative performance and efficiency between the media processing DSP and the GPU, and how you guide application programmers to map imaging onto one versus the other?
It's a really good question. We think about it all the time. It's case by case. Some algorithm really is friendly to be implemented in the GPU. We can move it to the GPU, but others, in general, the DSP can handle all kinds of cases, right? In the worst case, you can write the assembly code to parallel the things you want to parallel and to sequential the pipelines, whatever, any ways you can do in the way you want. But the GPU, we have a much more constraint. So to use the advantage, take the advantage of each processor, is not, let's say, we are doing it manually right now. Now there's no generic solution. We have to take a close look. Someone has to take a close look. Our vision was this work need to be done by the chip maker or OEM, not by the application themselves, application developer themselves.
Yeah. Yeah, I was going to ask if you could comment on the communication costs for taking, you talking about multi-core, about moving data from the different devices like CPU, DSP, GPU.
Mm-hmm. Okay, that's really another good question. You have got to have the data ready, then the processor can do something. If it's not, you have to wait. In general, we want to keep the data or the processing into the same core if possible. Only when you cannot handle it to move to another core. There is a cost in power, in the data traffic of bus associated with any sharing or parallel processing. Nothing is free. But ideally, when the framework of computer vision is available, those things can be handled automatically behind the scene. The apps developer don't have to deal with it. That's our mission in the industry.
The bad news is I have to cut off questions for support next, but the good news is you'll be at the demo table, right?
Yes, yeah.
So you can see
Please stop by.
Thank you.
Thank you.